Let's move on to multiplying vectors by a scalar. A vector and its scalar multiple are parallel. Let's take, for instance, vector v. Vector 2v has double the magnitude as vector v, but has the same direction. Scalar multiples not only can be positive in magnitude, they can also be negative as well. Let's consider our first example. A. Which of these vectors are scalar multiples of vector v? And explain. Well, here's vector v. What we're going to look for are other vectors that are parallel to v. They do not have to be facing or pointing in the same direction as v, but they do have to be parallel, and they're going to be different sizes. So in this diagram, we can conclude that A, C, D, and F are all parallel to v, and they are scalar multiples of v. Okay, so part B, find the scalar k for each scalar multiple in part A. So v, okay, we'll use v as our reference. The best way to do this would be to use a ruler. However, for time's sake, I think I'm just going to eyeball it. So we can say that C, k is equal to 1, so we're multiplying it by 1 because it looks like it's the same size as v. F looks like it's double the size but in opposite direction, so I'm going to say k in that case is -2. D is also facing the opposite direction but half the size, so k in that case is -0.5. And here A we'll say 3. So k for A is equal to 3. So in C part, which of these are not scalar multiples and why not? Well, that would be the vector E and B, and it's because they're not parallel to B. So collinear vectors. Vectors are collinear if they lie on a straight line when arranged tail to tail. The vectors are also scalar multiples of each other, which means that they are parallel to each other. So the following statements about non-zero vectors u and v are equivalent. U and v are scalar multiples of each other, such that u is equal to k times v. U and v are collinear. U and v are parallel. So all three statements are basically saying the same thing and are equivalent. We're just going to discuss very quickly vector properties. So vector properties for scalar multiplication is a distributive property. So the distributive property applies in which if you had u plus v times a scalar, then you can also say ku plus kv is equivalent. Associative properties do apply as well, and also the identity property for which a vector v times 1 is equal to itself. Linear combinations of vectors, when you're given two vectors u and v and scalar s and t, the quantity su plus tv is called a linear combination of vectors u and v. So we can express vectors as linear combinations of each other. Let's look at our next example. Let's take trapezoid ABC. Okay, in this trapezoid, BC and AD are parallel. AD is equal to 3 times BC. Okay, so we're going to let AB equal to U and BC equal to the V vector. We're now asked to express AD, BD, and CD as a linear combination of U and V. Now these are great questions. Let's see how this is done. Let's first take a look at AD. So the vector AD, we set up here, was AD is equal to 3 BC. BC is equal to V. So AD is equal to 3 times V. Okay, and remember, we're expressing these as linear combinations of U and V, okay, only. Okay, so AD is done. So BD, B to D. So let's do this. B to D. Okay, so there's B to D. So what we can do is find two vectors that will add to BD. So we can say BA, so there's BA, plus AD. Okay, so tip to tail is equal to BD. Yes. Okay, so what we have here is BA plus AD, okay, is equal to BD. So now AB is equal to U, so it's BA is negative U plus AD, which is 3B. Okay. Finally, let's look at CD. CD, let's draw this again on another CD in red. C to D is this vector right here. C to D. And again, we're going to find vectors that will add tip to tail with CD. Okay, so we can say C to B, so C to B, plus B to D, okay, C, okay, so B, BC plus BD will give us CD. Okay, so BC is equal to B, okay, and BD we had already determined to be minus U plus 3V. Okay, so that's CD. And that concludes our lesson for today, and we'll see you next time.